Hello guys, in this video we are going to talk about the map method or the maximum a posteriori method. So we discussed the ML method in a couple of videos earlier, and we saw why do we use the ML method. So we use the ML method to get the parameters. We want the parameters from the data. So we use the ML method to get the parameters from the data, and we saw that the ML method says just take the average of the samples and you will get your answer. So we talked about this graph also in one of my videos, and what essentially we are doing is we are calculating we are taking a constant mean. So we'll take, say, mean is equal to this first and try to fit a Gaussian and calculate the probabilities of these are the data samples. So calculate the probability of every data sample. So this is the mean and this is also data sample. So calculate the probability of this data sample with respect to this Gaussian, then this, then this, then this. You multiply all of them and you get your what we call as likelihood. So now there can be some cases. Say consider case 1 where you have, say, only 3 samples. So here you have less number of samples, and if suppose you were given with a lot of samples, they would look something like this. So this pencil denotes the large number of samples, and these points denote the the samples that we have. So in real world cases it may not be possible that you may have many samples. So it is possible that you have very less samples. 3 are really very, very less, but I am just giving an analogy and comparison. So here you can see actually the mean of this particular thing should be somewhere between over here, because there you can see there are a more number of samples are over here, so the mean of the samples may be somewhat over here. But according to the ML estimation, this is what the mean you would get, because what you would do essentially is you will find out the mean for every value of this x. So you will see you will take, say, a Gaussian like this which has mean over here. You calculate the probability for this sample, it will be somewhat here, over here, say 0.7. Then you calculate the probability of this Gaussian with respect to this sample. So let's see, this is 0.3. So like this, and then what you will do is slowly you will come at a point where you will get a mean over here, and when you see this you will get a better estimate. So for this curve, this probability will be close to, say, 0.001. This, for this curve, this sample value will be close to 0.001. I hope you can see the curve. Yeah. So this multiplication will give you a very less value tending to 0.001, suppose. But when you fit this curve, you will get essentially nice probability, say 0.7, 0.3, 0.3. So this will be, say, some 0.03, which is greater than this, and you will your ML, your theta ML will tell you that this is the good mean. But in reality, this should be the mean that you want. So let me denote it by pen. So in reality this was the mean that you want. It is just because of lack of samples that you ended up with this mean, right? So to come out of this problem, we are going to see what map method does. So this is also known as map method, MAP. So we'll see what the map method does over here. Also there can be a case where you have enough samples, but the distribution that the sample follows may not be a Gaussian distribution. It can be some arbitrary distribution. So here, say, you'll fit a Gaussian like this, but then since it is not the actual distribution, so here you will get the mean, say over here. So this is the mean theta ml that you have estimated, but then you can see for this data the mean should be somewhere over here at the middle. So this is the mean that you want, this is the theta that you want. So let me denote this also with a pen. So this is the theta that you want, but you are getting this. So for these situations, we can go for the MAP method, that is the map method. So the case one is that for less samples, so when your Ni, so remember when we were calculating the ML method, the ML method, we are doing the ML method, we had this Ni, number of samples, number of data, say number of images of sunflower. So when your data is less, when Ni is less, so for less number of samples, you can use the map method. So here the ML method starts failing. So here you can use this. Or if your assumption that the data is not Gaussian, is false, for that case also you could use the ML method, MAP method, map method. So here also the ML method starts failing. So let us see how does the map method does this. So in the ML method we were basically interested in this likelihood, and we saw that we can estimate the likelihood like this. But now if suppose we have some prior information about what the mean could be, so the question is how will you have this prior information? So say I, as a developer of the algorithm, I know how the sunflower looks. So I know that it looks like this, and say from some previous data or some estimation, I am giving it the information that if it is a sunflower, its mean would be something like this. The mean should be some mu naught. So please note that this distribution that I have plotted over here is not from the data. This distribution is not as like this, where I had data samples and I am estimating a distribution from the data samples. This is a distribution where I, as a developer or anybody who has some prior information about the particular class, say in this case sunflower, so I have some prior information about how many sunflowers are there in the world, in the nature, or something like that. So using that prior information, I have given this distribution to the algorithm. So here this distribution is not using the data. The data's distribution is coming from the likelihood, but this I am giving it a distribution. Okay, this is the distribution that the data is going to follow. You take this. So what happens is we are using the Bayes rule once again, and we are calculating the posteriori. So please note that the terms a posteriori and posteriori both are same. So if you remove a, it does not matter. Both of them are same in this context. So in this context, a posteriori and posteriori are the same. So please understand, this is a distribution that the developer or somebody else is giving to the algorithm. This I don't this is not from the data that we are estimating. So this is known. That is all I want to say. This is known, and still the things that are unknown is theta I. So we have to estimate theta I, and this p of theta I is known. So this p of theta I will also have a parameter. Suppose if this p of theta is also Gaussian distribution, so then it will have a parameter, say mu naught and sigma naught. So these parameters are known. We know these parameters by some research, or the developer is sure about it or something like that. We know these parameters, mu naught and sigma naught. So we are using the Bayes rule over here to calculate the posterior. So you have seen this equation. We have seen this from the start of the lecture, that this is the Bayes rule that we are following. So using the Bayes, so this is again the evidence, which will again we'll ignore this evidence. So all that we are going to calculate is just the product of the likelihood and the prior. So this is the likelihood, this is the prior, and we are going to calculate its product. So what we have this, we have the prior, and what we are going to do is we are going to multiply this probability, so this particular probability with this. Let us see how are we doing it. The algorithm is almost similar to ML. So what are we going to do? We are going to see if the mean is, if I take a Gaussian like this with say this mean, so we are going to calculate the probabilities for every sample. So say in this case we just have 3 samples. Over here we just have 3 samples. So here there will be this probability that will be calculated. So say this is 0.3, then you'll calculate this probability. So this is the ML method that I am saying. So then you'll calculate this probability, say 0.002, and this is some 0.00001. So this here, for here ML is quite nice. This will give a probability close to 0, so that will be okay. But then what we are doing in math is this thing, this particular probabilities, 0.3 into 0.002 into 0.00001 is further. So this particular product I am getting from here, the likelihood. So this is the product that I am getting over here. Remember that P of di given theta I had written as product from n is equal to 1 to ni, probability of xi n given theta I. So this product is this thing. We are taking the product for every sample, every in sample, and this is further multiplied by probability of theta I, that is the prior information. So if suppose this mean is over here, so that corresponds to a mean over here. Suppose this is the mean. So this mean, this value, say this is 2. So this mean value is 2. So say mean 2 corresponds somewhere over here. Please note that x and theta I are having the same unit. So this theta I is also, when it is the mean, it is having, it is the unit of size. So say size is in centimeter, so this is also in centimeter, this is also in centimeter. So we can actually compare them. That is what is happening over here. So here you, for year 2, this is even a less probability. So here say this probability is 0.02, so 0.002. This will further be multiplied over here. So this is the prior which is getting multiplied to the likelihood. So this was the likelihood, you are multiplying the prior. So this is further reducing the probability. Please understand how it is doing that. I will try to give a graphical explanation of this also. So please understand how this is happening. Now if suppose I take a mean, say like this. So this is a mean which is for which I will calculate the, so here this is the mean that I am calculating, the original mean, say. So for this probability I will calculate this probability, I will calculate this probability, I will calculate. So this probability will be, say nice 0.9, say this is 0.9, and say this is some 0.2. So because of this whole probability will come down, and say this is 0.9 into 0.9 into 0.2, so 0.018, so 0.18 into 0.2, which will be 0.036. So you see the probability went down because just of this factor. But this will in turn multiply with the prior information that we have. So say we, by our known distribution, the prior distribution, we knew that say the mean was this. By some we'll not say we knew the mean, but this mean mu naught will be close to what this is, what the true mean is. So this will be close to it. So say suppose this is the value that I am taking, so this is still having a good probability multiplication. So this will get multiplied by say 0.9 again. So this is say 0.9. So this will get multiplied by 0.9, and the final probability that you get will be higher. So there will be something like this. Now when you take a Gaussian like this, so now I am considering a Gaussian with mean this. So actually for theta ml this would have been the maximum, because then the probability over here, and these probabilities would have been multiplied. So this probability maybe say 0.3, say this is 0.3, say this is also 0.3, and say this is nice 0.95 suppose. So what for this particular mean you are having 0.3 into 0.3 into 0.95, which is again a very good big probability, which is nothing but say 0.0855. So this is a greater number if you would compare only the ML method, only the likelihood. This number we saw was very less, it was 0.036. For the actual true mean it was 0.036, but for this mean theta ml the probability was higher, 0.0855. but we don't want this, we actually want this something close to the true mean, right? So when this, if you see say this is over here, so this corresponds to some value over here say, so this is telling some value over here, so this will be say 0.3 over here suppose. So this in turn will get multiplied to 0.3. So by this multiplication you will get an answer say 0.02565. So this in turn will be less, because this prior is now acting and it is telling no bhai, this cannot be the mean, I know some data, I know some information about this, and this is not the mean, and it will tend to shift this to this. So this 0.036 into 0.9 is still giving you 0.0324, which is higher than 0.02565, and hence I will say that this is the mean that I want. So this will be theta map. Why is this? Because I am now, what I am going to do is, instead of maximizing this likelihood, I am going to maximize the posteriori. So because of this prior information that I have, that I am using over here, I am going closer to my true mean. So you can very nicely see what is happening over here. So in these sort of cases we use the maximum a posteriori method or map method. So one case is when the samples that you have, the data is less, and the other case is when say your distribution is something else. So when your distribution is not a Gaussian distribution, so that the assumption that we make that our distribution is Gaussian and hence we are modeling it as Gaussian, so when that becomes false, so at that time also your prior can do something. You can have your prior distribution as something close to this, because this distribution is something that is known to the developer and he is giving to the algorithm some prior information. So I would like to call this as God gift. So in humans you always tend to have some people who grasp things very fast, and they learn very fast, and then you say that they are God gifted. So I like to mention MAP method as giving a God gift to the algorithm. So you are giving this God gift, so you are a god of the algorithm, right? Because you are making him learn, you are making the algorithm. So you are giving this gift, your god gift, to the algorithm, because of which it gives nice results. So this was about the MAP method. So let me just stop the video over here. This is just an introduction. In my next video we will see what is how to generate the estimates, that is mu and sigma, for a univariate Gaussian distribution. So then now we are going to see if this is also Gaussian. We have assumed our likelihood also as Gaussian, so this is Gaussian. We are assuming this also to be Gaussian with some parameter mu naught and sigma naught. So this is some prior information that I have, a developer, my god gift, and we are going to see then what will be the estimate of mu. So we are just going to see the estimate of mean over here. The estimation of sigma will be quite difficult, so I'll upload it in say further videos, but not now for this particular course. Thank you so much for watching.